All right, this is the beginning of our probability unit, and so we're going to start out with just some pretty basic probability concepts today, starting with tree diagrams and area models and looking at some other kinds of probability. So first of all, first problem, bank contains a penny, a nickel, a dime, and a quarter. And you're going to choose 3 coins at random without replacement. And what that means is you're going to draw a coin, you're not going to put it back in the mix, and then you're going to draw the next coin. And then again, you won't put it back in the mix, and then you'll draw the next coin. Typically, things are done without replacement, and you should always assume that things are done without replacement unless I tell you otherwise. So if it doesn't say anything, it's not natural to pick it up, put it back in, mix it up, and grab it again. That's not the natural thing to do. The natural thing to do would be to keep it. So unless I tell you otherwise, you're going to assume without replacement, okay? So what you're going to do is you're going to make kind of tiers here. In this case, you could have a penny, a nickel, a dime, or a quarter, okay? So if you draw a penny the first time, then your next options are to have a nickel, a dime, or a quarter. If you draw a nickel first, then your next options are to have a penny, a dime, or a quarter. If you draw a dime first, then your options are penny, nickel, or quarter. And if you draw a quarter first, your options are penny, nickel, or dime. Okay, and then if you've drawn a penny and a nickel, then what you have left is dime and quarter. And if you've drawn a penny and a dime, then you have a nickel and a quarter left. And if you've drawn a penny and a quarter, then you have a nickel and a dime left. Okay, and I think you can finish this off. I am not going to finish it off right now. What you need to do then, so this is the tree diagram. That's the tree diagram. And then what you need to do after that is you need to list your sample space. And you get your sample space by following every path through the tree diagram. So there's one path right there. And then here's another path, and so on and so on. And so you're going to list your sample space, and your sample space will go like something like this. Penny, nickel, dime. Penny, nickel, quarter. Penny, dime, nickel. Penny, dime, quarter. Penny, quarter, nickel, penny, quarter, dime. Okay, and then I'm moving on. Nickel, penny, quarter, nickel, penny, dime, nickel, dime, penny, nickel, dime, quarter, nickel, quarter, penny, nickel, quarter, dime. Moving on to the dimes first. Dime, penny, nickel, dime, penny, quarter, dime, nickel, penny, dime, nickel, quarter, dime, quarter, penny, dime, quarter, nickel. And then lastly, the quarters first. Quarter, penny, nickel, quarter, penny, dime, quarter, nickel, penny, quarter, nickel, dime, quarter, dime, nickel, and quarter, dime, penny. Okay, I think I've got them all there. Notice there are 24 options here, 24 ways to draw 3 coins in our sample space. If you think about it, there's 4 coins the first choice, the first time you draw a coin, so 4 coins, and then you pick one and you don't put it back, and so then the next time there's 3, and then you pick that one, don't put it back, the next time there's 2, and 4 times 3 times 2 makes 24. Okay, so that kind of makes sense. All right, so down below now you're going to calculate some probabilities. You're going to use this sample space to calculate some probabilities. So I want to know the probability that 2 nickels are chosen, and because there's not replacement here, you can't get 2 nickels by drawing 3 coins. You could only do that if you did it with replacement, and I can't replace that coin, so there's no way I can get 2 nickels. So the probability would be 0. The chances that a quarter is chosen, and if you go back here, let's see, this has a quarter in it, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 of the 24 ways that have a quarter in them. So a quarter is chosen 18 out of 24 times, which of course we know reduces to 3/4. And then a dime is chosen first followed by a penny. And it doesn't say anything about the third coin, so that doesn't matter, but it needs to be a dime and then a penny. And so that's these two choices right here. You could have a nickel as the third coin or a quarter as the third coin, but dime and penny, there's 2 of those out of the 24 options. So 2 out of 24, which of course reduces to 1/12. I want you guys to rate these as fractions if at all possible. Most of the ones you're going to get in your homework today should be able to be written as fractions. Sometimes they're icky fractions and your calculator will only spit out a decimal. But remember to hit Math Enter Enter and reduce the fractions for me. You're going to have a half a point off on your quiz or your test if you do not reduce the fractions for me. So please make sure you do that. All right, the next one is tossing a coin, and people for some reason have a hard time making this tree diagram because they can't figure out how many options there are. But think about this. If you flip the coin the first time, you have 2 choices. You could get a heads or you could get a tails. And there's the first tier of my tree diagram. And then the next tier, so if I got a heads the first time, I could get a heads or a tails the second time. And if I got a tails the first time, I could get a heads or a tails the second time. Okay? And so assuming I went heads, heads, then the next time I could still get heads or tails. And so you just need to keep continuing making tiers to your tree diagram for every time you flip a coin. And it should look something like this. In your homework, you're going to get something similar with children, with boys and girls children, and you're going to follow the same kind of concept, okay? If I needed to flip a coin 4 times, I would add another tier to it by doing that off of each one. But I don't need to flip it 4 times, I only need to flip it 3 times. So if I list my sample space, these are all the things that could happen. I could get all 3 heads, I could get heads, heads, tails, I could get heads, tails, heads, I could get heads, tails, tails, I could get tails, heads, heads, tails, heads, tails, 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 heads, or all 3 tails. All right, and I want to calculate, first of all, the probability that you're going to get 3 heads. The 3 heads are all right here. There's 8 options total, which makes sense because there's 2 options every time you flip a coin. 2 times 2 times 2 makes 8. So all 3 heads, there is 1 out of the 8 options. That's all 3 heads. And then at least 2 tails. That means it could be 2 tails or it could be 3 tails. But at least 2 tails would be this one, this one, this one, and this one, all 3 tails. So half of them have at least 2 tails in them. 4 out of 8, or of course 1/2. Okay, so those are some tree diagram things. Then you need to know the formulas for these shapes right here. I'm sure you do know them, but in case you don't, I don't want to do you a disservice and make sure that you know them. So of course a rectangle or a square is length times width. A circle is pi r squared. A triangle is 1/2 the base times the height. And a trapezoid, this is one people have a hard time with, and circle, they get mixed up between that and circumference. But a trapezoid is the average of the bases. So it's 1/2 base 1 plus base 2 times the height. So if you don't remember those, go ahead and write them down. And I know this is a little fuzzy, but we are going to find the chances that if we were to drop a ball into the following regions, that it would land in a shaded one. So in this case, the shaded area is a trapezoid. And so if I find, first of all, the area of the trapezoid, I'm just going to do this for the area of the trapezoid. You know that this is 4, that's one base, and this is 6, that's the other base, and here's the height, which is 4. So the area of the trapezoid would be 1/2 the average of the bases times the height, and you would get 20 there. Okay? And then the total area is the whole outside square. Whoops. And the total area in this case would be 8 times 8, which is 64. And in this case, the shaded area is the trapezoid. So if I want to find the probability, I would do, in this case, the trapezoid, because that's what's shaded, over the total, which is 20 over 64, which reduces to 5/16. So there's that one. All right, moving on. We have the area of the circle. So the area of the circle, I'm going to do this for area of the circle. again, the circle is pi r squared, and so in this case I will have pi times 2 squared, which we know simplifies to 4 pi. And then the total area is a rectangle in this case, which is 5 times 8, which is 40 centimeters squared. And then the probability that it lands in the shaded, in this case, the shaded area is the circle over the total. So 4 pi over 40, which of course reduces to pi over 10. And I would actually prefer it if you would leave it in terms of pi instead of giving it to me as a decimal. I'm not even sure what the decimal is, and I don't have a calculator on me right now. But leave it in terms of pi. That's as simple as you can reduce it, and that's the most exact answer that you can give me. All right, and then this one is a little bit different for a couple of reasons. First of all, I need to find the area of the triangle. And in order to find the area of the triangle, I have to take half the base times the height. Well, it's clear that the base is 2, but the problem is I don't have the height. Okay, but I do know that this is an equilateral triangle because they're marked right here. So I know that this is 2 centimeters, and I know that this is 2 centimeters. And I know because it's equilateral that I can split this in half right here. So I know that this much is 1 centimeter. And so you can do a little Pythagorean theorem right here. You know that that's a right angle. And you can go 1 squared plus x squared, that's my height in this case, equals 2 squared. So 1 plus x squared equals 4, or x squared equals 3, or x is the square root of 3. Technically positive or negative, but we're talking about height here, so it's got to be positive. So my height then is the square root of 3. Okay, so to find the area of the triangle again, I'm going to take half the base, half of 2 times the square root of 3. Those are going to cancel, and I'm going to get the square root of 3. Okay, then the total in this case is the outside of the triangle, and it is a square, so it will be 10 by 10, which is 100. And then in this case, the shaded will be the total minus the triangle, which will be, in this case, 100 minus the square root of 3. And you can get an equidecimal for that, but I would prefer that you would just leave it like this in exact answers instead of trying to get decimals and rounding and whatever. Okay, so then the probability that it will land on the shaded, again, will be the shaded area over the total, which in this case will be 100 minus the square root of 3 over 100. And you can't reduce that anymore. I would prefer that you would leave it like that instead of as a decimal. That's the most exact answer you could give me. Okay? All right, now we're going to move on to some other kinds of probability. Probability of some compound events, some things that have to happen either simultaneously or after each other or whatever, and we'll talk about this in a minute. First of all, when you see the word or in probability, it means to add it and to take out the overlap. If you think about a Venn diagram, and this is what a Venn diagram looks like, and this is A, and this is B, and you'll see this on the next slide. But that or means this could happen or this could happen. Anything in this circle could happen or anything in this circle could happen. But the problem is that you've counted this area in here twice. So you're going to add everything in here plus everything in here, and you're going to take out the overlap. Okay? So that's what you will do in this case, and that's if things overlap. And sometimes things do overlap, like in a deck of cards, you could have the number 3 and a heart on the same card, so they overlap. And that's what you're going to need to do if they overlap. If they do not overlap, then they are considered to be mutually exclusive, and that's what's over here. And things like this. You can't have a king and an ace on the same card in the deck of cards. So drawing a king and drawing an ace would be mutually exclusive, but drawing a king and drawing a heart are not mutually exclusive because they overlap. Okay? So here we go, from a deck of cards, and hopefully you know your cards well enough. If you don't, you know that there are 13 hearts that are red. There's 13 of them. Okay? There are 13 clubs that are black. There are 13 spades. These are spades that are black. And there are 13 diamonds that are red. Okay. And then you know that they go ace 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king within each suit. Hopefully you know that. Okay. Anyways, all right, from a deck of cards, first of all, you need to know you're choosing one card and one card only, and that makes a difference. And I want to know the probability that you would draw an ace or a king. Okay, an ace or a king. Well, there are 4 aces and there are 4 kings. And you can't have an ace or and a king on the same card. So these are inclusive, or yeah, exclusive, mutually exclusive events. Okay, can't happen at the same time. You can't have an ace or a king on the same card. So there are 4 aces and there are 4 kings. So that means there is 8 out of the 52 cards that are either an ace or a king, and that reduces, if you press math enter enter, to 2/13. Okay, but now if you do an ace or a spade, there are 4 out of the 52 cards that are aces, and there are 13 out of the 52 cards that are spades. Okay, and then the problem is there are some cards that have an ace and a spade on them. There's one card that is the ace of spades. You've counted that as part of this set, and you've counted that as part of this set. So you need to take that overlap out of there and subtract that one out of 52. And when you do that, you should get 4/13. Okay, then a club. So a club is this, or a face card. So there are 13 out of 52 cards that are clubs. People always ask me about face cards. Face cards are only jacks, queens, and kings. That's it. Aces do not have a face on them. They are not numbered either, and they do not have a face on them. But jacks, queens, and kings are the only face cards. So there's a jack, queen, and king of hearts, of spades, of clubs, of diamonds. So there's 12 face cards out of 52. And then the problem is there are some face cards that are both clubs and a face card. Okay, so that would be the jack of clubs, the queen of clubs, the spade of clubs. Sorry, did I say that wrong? The jack of clubs, the queen of clubs, the king of clubs. And so there are 3 of those 52 cards that you've counted in both sets, and you need to take that overlap out of there, and you'll have 11 out of 26. Okay. And then lastly, a red card or a face card. There are 26 out of the 52 cards that are red. We've already talked about how there's 12 face cards, a jack, queen, and king of each suit. So 12 out of 52 cards that are face cards. And then you need to take the red face cards that are overlapping each other out of there. So there's a jack, queen, and king of hearts and a jack, queen, and king of diamonds that are red. So you need to take those 6 out of 52 cards out of there because you've counted them twice. And that gives you 8/13. All right, then you have a student selected at random from a group of 12 male and 12 female students. There's 3 male and 3 female students from each of the 10 grades. Find the probability that whatever. Okay, so here we go. A 9th or a 12th grader. So there are 6 9th graders, 3 male and 3 female, and there are 6 12th graders, 3 male and 3 female, which makes 12 out of 24 total, either 9th or 12th graders. And you can't be both a 9th and a 12th grader. So those are mutually exclusive events, can't happen. You don't need to take any overlaps out of there. You don't need to worry about it, and you get a 1/2 probability. Okay, a 10th grader or a female. So there are 6 10th graders, 3 males and 3 females. So there are 6 10th graders out of the 24. And there are 12 females in this bunch. So 12 out of the 24 people are females. But then you need to take out of there the 10th grade females because you've counted them in both places. Okay? So there are 3 10th grade females out of the 24, which gives you 5/8. And then the last one, male and not an 11th grader. So again, there are 12 out of 24 people that are males. there are 6 11th graders, so that means there's 18 of 24 that are not 11th graders. And then you need to take the male not 11th graders out of there. So the male 9th graders, there's 3 of them. The male 10th graders, there's 3 of them. And the male 12th graders, there's 3 of them. So there's 9 male students who are not 11th graders that you've counted in both sets. And so you need to subtract that out of there, which gives you 7/8 when you reduce that. All right, then sometimes you're going to see the word and in probability, and means both things have to happen. Not one or the other, but both things have to happen. And so if you're looking at a deck of cards, and I want to figure out the chances that you're going to get 2 kings. So first of all, the very first card, what you're going to do is this. There's 4 out of the 52 cards that have a king on them. If I do with replacement, that means I draw a card, I look at it, I got a king, there's a 4 in 52 shot that I got a king, I put it back in my pile, I mix it all up, and I draw again. So the next time when I draw, there's still a 4 in 52 chance of getting a king. And I am going to multiply these two things out and then reduce it, and I should get 1/13. The difference between that and then when it's without replacement, and again, it's typically without replacement. So unless I tell you it is with replacement, assume that it's without replacement. But here's the difference. There's 4 out of 52 cards the first time I draw a king, the chances that that will happen. Then if you pick that card up and you got a king and you look at it and you keep it and you don't put it back, the next time there's only 3 kings left and there's only 51 cards in the deck left. Okay, so that's what that would look like. And when you reduce that and multiply it, you are going to get 1/221. All right, a couple other situations here. This time I have a cooler in it. 3 cans of Mountain Dew, 4 cans of Pepsi, 3 cans of Dr. Pepper. I want to know the chances that, first of all, I get a Pepsi. So there are 4 cans of Pepsi out of 10 cans total. Notice I didn't say anything about replacement, so you're going to assume that it's nothing is replaced. So the first time I got a Pepsi, now there's only 9 cans of pop left, so be careful about that. But if I drew a Pepsi the first time, then I haven't drawn any Dr. Peppers, so I still have 3 Dr. Peppers left. Then the next time I draw, there's only 8 cans of pop left. But I already drew a Pepsi over here, so I started with 4 cans of Pepsi, but you're going to assume that you drew a Pepsi here, so now I only have 3 Pepsis left. Okay, and when you multiply that all out and reduce it, you should get 1/20. All right, a die is rolled and then a spinner is spun, and so when you roll a die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. Okay? So of those, the prime numbers, 1 is a prime number, 2 is a prime number, 3 is a prime number, 5 is a prime number. So there's 4 out of 6 numbers that are prime. And then if I spin this spinner and get a yellow, it's supposed to be equal. It might not look quite equal, but it is supposed to be equal. 1/4 of that circle is yellow. And so when you multiply that out, you should get 1/6. You have a 1 in 6 shot of rolling a die and getting a prime number and then spinning the spinner and getting a yellow. And both of those things have to happen. When it's and, you multiply. All right, now we're going to toss a coin, and again, we did the tree diagram before, so if you needed to do the tree diagram, do the tree diagram. I'm going to just list the sample space, which is heads, 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 tails, heads, tails, heads, heads, tails, tails, and then tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. All right, so first of all, I want to know the probability that if you toss a coin 3 times, you'll get 3 heads. And there's only one of those, and it's right here. So there's a 1 in 8 shot that you'll get 3 heads. Okay, that you'll get 3 tails is the same thing. Only 1 out of those 8 outcomes gives me 3 tails. No heads, the only way I would get no heads is if I got all tails. It's the only way I would get no heads is if I got all tails. So we know that that is still 1/8. Okay, hopefully none of these are going to be too much of a problem. I am going to just bring these down here. All right, now I want to know the chances that I get one head. Notice that I did not say that that head had to be the first one flipped. I just said you had to have one head somewhere. It does not have to be the first one. So if I'm asking you for where there's one head, that would be here, here, and here. Okay, so you have a 3 in 8 chance of getting one head. All right, heads, tails, tails. That is, there's only one option there, heads, tails, tails, and that's right here. All right, and then here's where people have trouble. Anytime you see these two words, the words at least, people get a little bit stuck. So I'm going to try and explain this the best I can, okay? But at least one head means you could do this. That means you could have one head, or you could have two heads, or you could have three heads, okay? That's it. That's what you have to have if you have at least one head, okay? So if I have one head, that means I can count this option, and this option, and this option. So you have a 3 in 8 chance here. Or remember, in probability means to add, okay? Two heads would be 1, 2, 3 right there. So you have a 3 in 8 shot of that happening. Again, or in probability. And then three heads is this one. Okay, so three heads is a 1 in 8 shot. When you add that together, you get 7/8. Okay, now that's the long way to do this. I want you to notice that the only thing we have not chosen is this one right here where we have all three tails. So the shortcut to do this, whenever you see these two words at least, the opposite of having at least one is to have none. Okay, so what you could do instead is to do 1 minus getting no heads. And we calculated that probability up above, and the chances that you'll have no heads means basically the chances that you'll have tail, 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 or 1 minus 1/8, which is also 7/8. So this is kind of the short way to do it. But you do it whichever way you feel comfortable. Either one of those will work, but those two words at least, think of it being the opposite, or else you have to add all your options up. Either way. Okay, so that should do it for this day.